science of climate change is about molecules of some substances in the atmosphere. Those particular substances that we call greenhouse gases, and they're the ones that affect the energy balance of planet Earth. The most notorious of these, the ones we read about every day in the newspapers and in the scientific literature, is carbon dioxide, whose molecules have the formula CO2. But there are others, in particular methane, oxides of nitrogen, and naturally occurring water vapour. Why is it that carbon dioxide gets so much attention? It must be pretty important. Well, of course it is. And that's because carbon dioxide is the product of combustion of fuels. The fuels whose molecules contain carbon atoms that we call fossil fuels, or carbon-based fuels. For example, when, even at home, ordinary natural gas that we use on our cooktops is essentially methane. And the reaction of combustion, which is a reaction with oxygen, produces carbon dioxide. I can approximately represent the burning of petrol in cars by the burning of octane. Petrol is a mixture of many substances. We just use this as an example. When it burns, reaction with oxygen, it produces carbon dioxide. That fossil fuel that is the subject of much discussion, coal, consists of molecules which are very large and different from place to place, from grade of coal to grade of coal. In one particular analysis, the molecular formula of one grade of coal was determined to be this large molecule with formula with 169 carbon atoms in it. You're reading this formula, at each of these corners here there's a carbon with a hydrogen atom attached to it, implied but not shown. So when that substance burns, and do a bit of stoichiometry as we've done in the past, if it burns in the presence of plenty of oxygen so that all of the carbon atoms are converted into carbon dioxide, we can do some simple calculations. You can do a bit of calculation on this to work out that the molecular mass is 2,378 grams per mole. We only need enough of the chemical formula, the balanced chemical formula, to know that one molecule of this particular compound in coal will produce 169 molecules of carbon dioxide. We know that one mole of each of these is 44 grams. One mole of each of these is 2,378. 169 of them, so 2,378 produces 7,436 grams of carbon dioxide. That many kilograms of carbon dioxide. That many tons of coal, that many tons of carbon dioxide. A medium-sized coal-fired power station per day burns about 10,000 tons of coal. That means it shoves into the atmosphere 31,000 tons of carbon dioxide per day. And that's just one medium-sized coal-fired power station. Think of how many such power stations there are around the world. And on top of that, add the amount of carbon dioxide coming out of the exhaust pipe of our cars, and all the places where we need coal for engines like production, like refining, like extraction of metals, like transport, like electrification, the lights in our houses and down the streets. And the reason that these reactions are important is because those combustion reactions are highly exothermic, and energy is released, and it's that energy that we are harnessing. And of course, energy needs have increased rapidly over the years, the last 300 years. of the Industrial Revolution. We're producing more and more for more and more people, and so there's more and more carbon dioxide being released into the atmosphere. So the concentration is increasing. Aussie? So, Prof, if there was no need for all this energy before the Industrial Revolution, there was no need for all this industrial level combustion to provide that energy, then there was zero carbon dioxide in the atmosphere before the Industrial Revolution? Well, in fact, I was just going to address that question. And of course, there's always been carbon dioxide in Earth's atmosphere because we can't have life, neither plant life nor animal life, without carbon dioxide for the processes of photosynthesis and respiration, if nothing else. It's always been a part of the carbon cycle. It's a bit embarrassing. Sorry. Don't be embarrassed about asking questions, about thinking, about clarifying. Never ever be embarrassed about that, Aussie. So in fact, millions of years ago, there was a much higher concentration of carbon dioxide than there is now. And over the years, natural processes have reduced that. But I'll give you some context first. The age of the universe, the time since the Big Bang, is about 14 billion years. Planet Earth has been around for about 1/3 of that time. We, Homo sapiens, have been around for about 1/4 of a million, not a billion, 1/4 of a million years ago. That's only 0.005% of the age of the Earth. We are very, very much Johnny-come-latelys. And the Industrial Revolution is not 250,000 years ago, but about 250 years ago it got underway. So we're talking about very, very recent processes. So we talk about what the concentrations have been over the years, but more particularly what it was just before the start of the Industrial Revolution. Fossil records suggest average temperature 250 million years ago, about as far back as good records, good analyses can take us. We're about 10 degrees higher than they are now, average, on the Earth, and carbon dioxide concentrations about 5,000 parts per million. Natural processes, decreasing volcanic activity, formation of oxygen, dissolving of carbon dioxide in the oceans, increasing forestation, absorption of carbon dioxide in the photosynthetic process, levels have reduced. And over the past nearly a million years, carbon dioxide molecules have been going up and down, fairly stable in the range 150 to 300 parts per million, a long way lower than it was on baby Earth. Map here to read this. This is parts per million of carbon dioxide being estimated in the air. And the temperatures relative to this line here, talking about the standard in the time period 1850 to 1900, taking that level there, what was it in the past? So the carbon dioxide concentrations were much higher. They've been coming down during those processes happening as I talked about. This is a logarithmic scale, not linear, going back to 500 million years ago. And over this period here, the concentrations have been relatively constant at about 270 or so, somewhere between 300 and 150 parts per million. The start of the Industrial Revolution, the average concentration in the atmosphere was about 270 parts per million. 270 molecules per million molecules total. That's mainly oxygen and nitrogen. Put another way, 0.027%. So in a sample containing 1 million molecules, nitrogen and oxygen, there were only dispersed amongst that about 270 molecules of carbon dioxide. We know the temperature was pretty constant in the quite some time before the Industrial Revolution got underway, so it must have been a condition of energy balance. And the energy balance at that time was happening in an atmosphere with that concentration of carbon dioxide molecules. And just by the way, and this is very important in our discussions later on, it's now 422 parts per million. There's been considerable change. We'll come back to there. So, that's where we're going. We'll relate things to that 175 parts per million. I remind you that we haven't discussed how we know, how scientists know what those concentrations and temperatures have been in the past. That's a very, very important story for another time. Now, I'll leave you with some thoughts. Is it possible that just a few hundred carbon dioxide molecules dispersed amongst every million molecules of nitrogen and oxygen can affect Earth's balance, energy balance, significantly? I probably wouldn't be asking the next question unless the answer to that one was yes. How? Why? And then leave you with the thought, is carbon dioxide in the atmosphere a bad thing or a good thing? We'll talk about that soon.